Hey, my name is Rauiri, and you get the second session with me today. Hopefully this time I'll be a little less nervous and make more bad jokes. So I'm here today to talk to you about rebuilding the data center. Who am I? I've been working in networking since I've been about 16, professionally for the last I don't know, well over a decade. I've worked big scale, small scale, and I wanted to give you guys a presentation about what I wish somebody told me a decade ago. If you want to send corrections, contact, there's my email address. If you want kitties, there is a whole bunch of cat gifs on Honest Cat Worker, a very lame parody of Honest Networker, which is awesome. So, who is this for? Well, anyone who has an interest in the data center. This is not an exhaustive look at vendor landscape. This is really just a nice light guidebook in what's happening in the data center space right now. Who is this not for? Well, basically anyone who is a vendor, sorry. If you already have a deep knowledge of the data center, you can just sit back and enjoy the cat gifs. And what we're going to do for the next 40 minutes, we're going to talk about this. We're going to have a very quick tour of the landscape right now for ASICs. A very quick look at what network operating systems are out right now. A quick touch on protocols. A brief overview of config management, and then we're going to have a little bit of an incoherent view of slapping it all together. And cats. Gotta have cats. So, like I was saying, this isn't really exhaustive. This is just nice and light. I mean, it's been a long day. I'm sure we're all thirsty as well. I'm not affiliated with anyone. This is just all on my own from being involved and from just looking at what's happening in the community. I have not talked about vendors, like I said. Anyone who's doing everything in-house, they won't appear here. All I want is just to give you guys a little bit of a framework for what's happening in the crazy world we live in networking only. So, last 5 to 10 years have been really interesting in networking. We have seen that the traditional approach is not really working so much anymore. White box is growing crazily, like really, really crazy. The traditional vendors are really not keeping up. I mean, if you saw, I think it was recently Cisco were down to just above 50% market share, down from 75 in 5 years. So they're really losing space here. And it's really cool because today it's just like a server. You can go pick your ASIC. You can ask a manufacturer to make it for you with a reference design. You can pick whatever operating system you want, layer it on top, and then you can pick whatever configuration management you want. It's really, really nice, actually. So let's get started. So like I said, let's do a quick tour of the ASICs. I hope you guys know what an ASIC is. It's basically like the brains in a switch. It does all the hard lifting, the forwarding. Generally, you have a few manufacturers, and they give a reference design, and then the reference design is made by an integrator or a manufacturer. It's kind of like how Dell deal with Intel. Actually, it's the exact same as how Dell and Intel work together. So there's 4-ish players, and I say ish because there's a lot happening in this market right now. We have one incumbent dominating player. We have a few more smaller players. We have one exiting the market, and we have a lot of startups that are making references and making ASICs. This is more or less to help you guys when you start thinking about beige box. Now, beige box is white box switching from an integrator. So Arista is the classic example. Cumulus recently became a beige box because they're now an integrator, so they sell the hardware and the software together. And this is hopefully something to help you guys understand what's happening. So the main foundries I was talking about, we have Broadcom, who absolutely dominate the market right now. We have Cavium, who are been around for a while, but I think they're going to start seeing an uptick. We had Intel. Sorry, we had Intel as an ASIC foundry. They bought Fulcrum Networks, I think it was, and acquired ASICs that way. And we have Mellanox, who have been around for quite some time, but they're starting to become relevant in the Ethernet space now. So like I said, Broadcom dominate the market right now. They have two main lines. You have June. You'll see it referenced as Strata DNX. This is mainly like service provider style ASICs. They have big TCAM. They're more suited for routing, not switching. Jericho is the one that's making a lot of noise right now because this is the first white box chip that will take a full internet table. So this is really changing the market. It's really, really cool. We've Qumran, which is just about to be released as well. More or less the same. There's differences between Jericho, but it's aimed at SP style applications. And I've seen reference to Kalia, but I don't know anything about this yet. This is sometime in the future. And then the other line of family we have is the Strata XGS. These have been around for about 10 years now. Trident was the most famous. Tomahawk is the recent evolution here. It's mainly for switching a data center, top-of-rack style stuff. Cavium, like I was saying, have been around for a while. They just released the XP-Lint XP80. I think it's just Arista 7160 that has this on the market right now, but I'm sure there's other reference designs going to show up soon. And we have the Octeon 5000. This little baby, you've probably used it in the Juniper SRX. So it's been around for quite some time. And like I was saying, we have Intel who are exiting the market from what I can see. We had the FM6000. Then there was supposed to be the follow-on, the FM10000. It never showed up. It went missing for a while, and then it became a NIC. So that was kind of sad. I was looking forward to seeing that ASIC hit the market. And these are all this is all for switching. These are top-of-rack type applications. And Mellanox, who I said recently I started to become relevant. You have the Spectrum ASIC. It seems to have very good performance, something akin to the Tomahawk from Broadcom. And I have the Switch X2, which is kind of like old. Not really much to say about it. So I have a reference slide here for you guys, just to say what we covered here and their performance. I'm not going to read out the stats for you. You can look at it as a reference later on. The thing I would like to point out, though, is there's a couple of question marks, and this is because the data is just not there, or it depends. So one of the nice things, or one of the really cool things right now in the space is, like I was talking about Jericho, it doesn't have a fixed buffer. There's on-chip buffer, but you can expand it with just DDR memory, like off-die. So you can put in whatever you want. I've seen designs with 8 gigabytes of buffer, which is really cool. You can do the same with TCAM. It's expandable. There's 1 million roots plus. But like I said, this is more a reference for you guys for later on. So now we've covered the boring chips. We'll go on to the operating systems. So the space is a bit interesting. There's both closed and open source. There's quite a few players, and this has been driven a lot by OCP and Facebook for the Open Compute project. You buy your switch, like I said, and you pick your operating system. Generally, you'll use 1E as a booter, or a loader, and then from there you can pick an operating system of your choice. For operating systems, a lot of the times I'm going to have to refer you to sales, because, like I said, a lot of these are commercial, which kind of sucks, but we'll get there eventually. I'm going to talk about 4 main players right now. The Arista C EOS, that's containerized EOS, which is released 2 weeks ago. Cumulus, who have been in the market for quite some time. OpenSwitch and SnapRoot. So Arista released this recently. It is they've decoupled their operating system from their hardware. You can now buy EOS, and they press release claims it'll boot on white box switches. It's too early to see what's going to happen here, but I am optimistic about the future here. And like I said, you can ping your local SE who's sitting in the back here. He'd be more than happy to answer your questions. If you want to play with it more, you can also download VEOS, which is EOS in a virtual machine. Cumulus have been around for a very long time. They're very mature. They are deployed in some of the bigger networks, bigger cloud networks. It's basically a fancy Linux box. The switch ports show up as interfaces. And again, unfortunately, you got to go with bug sales to get like some more information on this. Or you can download VX, which is the operating system in a VM. OpenSwitch is the only open source one I'm going to be talking, that's on this list. It's quite like Cumulus, so it behaves like a Linux box. This time, though, you can actually just go directly to GitHub and see what's happening. And FlexSwitch. These guys are only after coming on my radar in the last few months. They seem to want you to configure the entire device with JSON via RESTful API, which I think is really, really cool. It's got a pretty cool hardware compatibility list, but unfortunately, again, sorry, you're going to have to go bug sales to get your hands on this. So we're going to go get the party started. The main thing about the data center is the protocols that are running. We always aim to try to build a simple data center. It's from RFC 1925. Its perfection is not when you've put everything in, but when you have nothing left to take out. We should always, or we only think about routing and switching in a data center. We don't think about like fancy services. Recently, we have seen a demand for overlay because of vMotion from VMware kind of required layer 2 adjacency. So now we're kind of in a position where we're transporting layer 2 further than we should. But like I said, luckily with an overlay, it's back to switching and routing. So I'm going to talk about VXLAN today, a little bit about ECMP, touch on Trill and SPB, and then the stables of OSPF BGP. VXLAN is basically an overlay. This was the answer to the problem of vMotion, which requires layer 2 adjacency, and actually layer 2 adjacency in the data center in general. So basically, it's just MAC and UDP. The simplified way is you take your MAC, your layer 2 frame, and shove it into a UDP and send it to somewhere. It's very useful to route your switching, which kind of makes no sense, but stick with me. And we're starting to see it evolve to a good DCI. So traditionally, to get data center or layer 2 between data centers, we either bridged, which is not fun, or we went to MPLS-based services. But now we can just use very cheap switches with VXLAN to transport your layer 2. It's pretty cool. So basically, VXLAN just bridges traditional layer 2 into what's called a VNI, which is like a VXLAN, VLAN basically. First generation of hardware only allowed switching, so you just switched stuff. Later generations started to do routing. This seems to be some kind of like dark arts on the modern ASICs, but it seems to work. But the only thing you need to really consider about VXLAN is how you do MAC address learning. So VXLAN itself doesn't talk about like how you learn MAC addresses. It just transports stuff. So you need to take a few minutes to wonder if you're going to do classical flood and learn, so multicast basically, or in Linux case, it's like you have a list of unicast, like other VXLAN speakers, and then you just send the MAC addresses that way, or the frames that way. Or what we're seeing right now is the current thinking is head-end replication. So you're going to use BGP and EVPN, and use that to like learn MAC address and ingress, and then program the network with the MAC address. So you distribute the MAC address via BGP. So also going to talk about ECMP. This is one of my favorite things. It's basically a load balancer for free from the network. It's It's equal cost multipath. It's layer 3 multipath. It allows you to use multiple interfaces and forward over them. So we didn't use this in the past because rooted ports were expensive, but now they've been coming down since we have an open landscape with cheap ASICs, cheap providers. We started to be able to do ECMP. You can go 128 wide, which is extremely wide. So you can effectively scale horizontally, so you don't need to buy bigger interfaces anymore or hit that limit of 8 interfaces in a lag and then can't get more. So ECMP itself is not really a protocol, it's more like a mechanism to distribute traffic. It relies on the protocols, the upper level protocols, to distribute prefixes and calculate what is reachable. Basically, if the routing protocol considers the paths to be the same, they're the same, and the hardware installs all the routes that have valid next hops. And then it's just a matter of deciding how you're going to distribute your traffic. If you're going to use layer 2 information, layer 3 information, and or layer 4. So basically, do you hash a TCP session on one path based on source destination port and source destination IP? I'm going to briefly touch on layer 2 multipath. Myself, I have not seen this deployed, so I can't really vouch for it. It's also interesting because I've only seen the major vendors implement layer 2 multipath. I found some Linux repo that was unloved, that had the start of a Trill implementation, but it seems to have died slowly, so I don't really see this making a major impact on the future. So basically, we can talk about the pros and cons of layer 2 multipath. And like I was saying, there's no real implementations out there that are based on open network operating systems. You mainly have to buy into a vendor with a solution, which sucks because then you're in a situation where you're lock-in. And also, as to note, I think it was SPB. One of the main implementations is Avaya, who have been recently acquired, I think. So doesn't really give you warm fuzzy feelings for the future of the protocol. And also, it basically allows you to scale your Ethernet, but as we know, scaling Ethernet is problematic, especially with ARP resolution. So it doesn't really solve the failure domain problems. It just actually increases the failure domain, which is not good. But in a data center environment, it's not good. But SPB is quite good for Q and Q. It'll use the inner and outer tags to hash traffic, so you can actually get a good fan out. It plays nice with regular switching, so that's cool. And it is still growing. The vendors are still putting effort in here. And now we're going to talk about BGP OSPF, which I hope we don't need to introduce. It's just quick comparison of link state and distance vector. Basically, what we're going to talk about is pros and cons, and then later on we'll talk a little bit about why we pick one over the other. So as it stands right now, OSPF seems to be a good choice in smaller data centers. IS, which I hope doesn't put me on a watch list somewhere, is definitely an ISP technology, although I've heard that Facebook use it in their DC. And then we have BGP, which is slowly taking over everything in the data center because it does, like I was saying earlier, it does EVPN. It'll allow you to do tenant isolation, so VRFs. You can also do unequal cost multipath, which is really, really cool actually. You can also filter per node, and you also have FlowSpec, which is touted as a protocol for minimizing DDoS, but you can also use it for other stuff as well. It has a rate limiting function. So a quick discussion about pros and cons. So if you've implemented a distance or a link state protocol, you know that you need a backbone area for OSPF, or what you call level 2 for IS. I know there is an RFC to allow hierarchical routing in areas for OSPF, but you still have the same common backbone area that needs to be unpartitioned. IS is a little bit more flexible, but you still have the same requirements. They're chatty protocols. They flood the link states everywhere. It's one of the fundamental requirements of a link state. You need full reachability from all nodes. It has some issues scaling. 10, 20,000 LSAs in the LSDB takes some time to recalculate. And it is a pain in the ass to troubleshoot. I mean, I was talking earlier about interviews. One of the classical questions is talking about LSA translations between like a stubby area or an NSSA. They're difficult interview questions because it's overly complicated. And this doesn't bode well when you're trying to troubleshoot something in a data center. Luckily, there is some positive things about link states. You can make them hierarchical. You can shrink your domains. Makes it like not too bad. Your traffic engineering tends to be consistent. You have to do it like, since your domain is a link state, it has to be like in sync with itself. It does reconverge fast, and it is well understood there is any amount of documentation you want on OSPF and ISIS. And for BGP, you no longer require layer 2 adjacency, which might be problematic if you're unfortunate enough to have SAN traffic. And traditionally, BGP was thought as complex. It was something that only the big or the senior engineers got, but thankfully that is changing. But BGP brings awesome things to the table. You have per node traffic engineering. Everyone is independent in BGP domain. They're all independent speakers. One can fall, and it should not affect anyone else. It is mature. It is very mature. It is easy to troubleshoot. You can see what your neighbors send you. You can see what you're sending your neighbors. You can see what the policy is you've applied. It is very nice, and it is very extensible, as we've seen. You can add address families, you can add types. It's wonderful. So now we're going to go straight into config management. SDN is one of my most hated words, sorry. It means absolutely nothing. In this case, SDN is going to mean automation. Automation is good. I like automation. I'm lazy. I don't want to do the same thing repeatedly. I want to do it once and just like let the machine do the work. It's really cool that we're starting now in the data center to be able to use the same tooling that we use for servers. So a switch is really just a fancy server with extra ports. So we can use the protocols out there, or the software out there today. Ansible is really cool. It's there. It supports most of the operating systems. It's a no-brainer basically to use. Salt and Puppet, they're all there. They'll all talk to networking equipment. I really like automation because it brings predictability to the table. There is nothing worse than you get paged at 3 a.m. and something has broke because there's a slight config drift because we did everything by hand in the past. So I really am a big proponent of automation. It makes things fast, very, very fast. And we finally get the idea of QA into networking, which I think we've been missing for quite some time. Yes. Automation is this awesome. You can just sit back and watch your network deploy itself. And I talk about Ansible, Puppet, Chef, and a little bit about OpenConfig. So I don't know if you have used these tools or encountered them before, but basically you work with the idea of data as a model. You define your data, and you don't really care about configuration anymore. So when you're configuring a BGP session, do you really need to know which vendors use which commands? It's just not really relevant. You need to know your IP addresses, your ASNs, and what policy you want to apply. This is the data you should be thinking about, or we should be thinking about. We don't really care what vendor does what on their CLI. And if you tie these into Git, then you make any kind of certification you might take, like PCI, you make it a very nice, easy experience because now you have auditing. So a quick note about the software I've mentioned, Ansible, Puppet, Chef, and Salt. Puppet is a bit of a strange one because it requires you to have an agent on your switch, so you need your your operating system provider to actually do some work. Ansible is something more like a push model, so you don't need the vendor to do anything at all. You just push config out the box. This is a small playbook, a snippet of a playbook. The playbook itself is just to provision the BGP sessions in a spine. You're seeing here is just a way to configure interfaces on Arista. It's very straightforward. I'm also going to talk a little bit about OpenConfig because I think this is really cool. It's relatively new. There's no full-featured deployment of it yet. It came about because a whole bunch of vendors or a whole bunch of big networks were really sick about this parser behaves like this. This Juniper is set commands. iOS is like this. iOS XE is a different way, and iOS XOR is slightly different again. They wanted a standard way to define and talk to their devices, so they started with OpenConfig. It's still incomplete. They're still working on the models for everything. BGP is more or less done. Interface is more or less done, so that's basically everything you really need, isn't it? After that, it's bonus. It basically uses Yang as the data model, and then netconf and a new protocol, RESTconf, to talk to the device. So you basically just, in Python speak, you just create a dict, dump it into a JSON object, and throw it at your device via RESTconf, and it's very straightforward. There's a very brief selection of what your config looks like for setting up a neighbor. It's pretty straightforward. It's going to be the same on every device. That is the promise, that all vendors should be supporting this, so you just talk OpenConfig from here on in. OpenConfig also brings streaming telemetry, which makes me happy because I hate SNMP. So instead of the pull model, you have an NMS that talks to your devices and pulls information back. All the devices just push state directly to a central point. So you have live, you no longer have this 5-minute monitoring window. You have real-time dynamic data on your devices, which is really, really cool. Now you're going to get a bonus round of 25 gig. I felt it was good to include 25 gig because it is relatively new to the table, and it's giving us something akin to Moore's law on networking. We're getting a 2.5x bonus, but basically free speed. So it's relatively new. Consortium found it up in 2014. I think it was Google, Facebook, Arista, and a few other players, Intel maybe. They decided that it was time to get rid of 40 gig, which is a horrible standard, and moved to 25 gig. Then the IEEE started their work on in a few months later. Quick note about distances and form factor. The original spec didn't have forward error correction, so you had limit 3 meter. The IEEE spec brings the FEC to the table. It gets you beyond the 3 meter, like a direct attached copper limit. You have active optical cables that will get you 30 meters. You have your standard multi-mode fiber SR, just like 10 gig. It'll do 70 meters OM3, 100 meters OM4, basically like a drop-in replacement for 10 gig. Same with single mode fiber as well. Get you up to 10K. You can do breakouts if you are so inclined. The form factor is exactly the same as SFP Plus, just known as SFP 2.8. You can do QSFP 28 breakouts as well, which would be, if you want to take a 100 gig port, you can break it out to like 425s. So finally, I'll try to bring this all together for you guys. We'll take a little stroll down history lane, get some thoughts, a little talk about topologies, and then taking it all together. So, like I said, I want this as more of a framework for you guys to just be able to see how to pick something in a data center. This exercise is going to be unique for everyone. I can't really help as much as I would love to. But I will say pay attention to the specs. There's some ASICs that can't do line rate under 100 bytes. You just do the homework. But once you have picked all this wonderful stuff of ASIC, manufacturer, operating system, you can probably need to connect it together and probably configure it. So when we are choosing these vendors, some of the driving factors right now in the modern data center is like horizontal scaling. So before we used to buy big ass chassis, big ass line cards, and just try to scale vertically. But we ran out of capacity, mostly because we were using spanning tree, which is a horrible protocol, like I said already. But now, if we go ECMP, we can scale vertically. We no longer have to buy the biggest box. Sales engineers are probably sad, but that's not our problem. We want to minimize failure domain, so tiny amounts of layer 2, compartmentalized routing protocols, make things small, make them fail quickly, make them fail without breaking everything. You also would probably want to pick a routing protocol that has easy implementation in code, which means less bugs, and operational support, so usually a single data type, not like OSPF or ISIS. And there's another driving factor that I think is going to be paying a lot more, it's going to drive a lot more in the future, so location independence. We've started to see large scale Kubernetes or Docker deployments. These have a unique challenge on the network because they make reachability a real pain in the ass. Luckily, with some overlays, it makes it a little bit easier, but at the same time, we should be able to let servers announce their reachability into the network rather than have the network force location and reachability. So I think this is important to keep in mind. So how do we used to do things? We used to use something called a fat tree, which is a subsection of CLO topology. It's basically your standard core aggregation distribution layers. It's a lot of stretched layer 2. It's hard to scale out. It has bad bisectional bandwidth. I mean, getting from one side of the tree to the other side of the tree means you need to traverse up the tree and down the tree, and that is expensive and creates choke points, basically. We didn't really deploy routing protocols very well. We used to use link state. It kind of sucked, to be honest. This design was assuming that most of your traffic is north-south, so your servers talk mostly to the internet, so for every, out of 100 bytes, 10 is going to traverse to the internet, 90 is going to stay inside of your data center. And usually this was a large common failure domain. You needed as you go up the tree from aggregation to distribution to core, you needed increasing amounts of reliability on your equipment. Out of this though, a few things worked. Ethernet. If any of you have had the misfortune of fiber channel or fiber channel over Ethernet, I am so sorry. InfiniBand, same deal. Let's just stand on one protocol and just work with it. Ethernet was the one because it's cheap, it works. Homogeneous network topologies worked, predictability is important. Minimizing layer 2 also helps me sleep at night and is good. And active setups were always a better idea over active backup, which is, again, more of the reason I hate spanning tree. And open standards. Open standards has always been the way of networking. From the start to till today, it's even more important now where we have vendors that are trying to push closed lock-in solutions. We should always go for open when we can. What didn't work? Like I said, mixed media. So Ethernet, fiber channel over Ethernet, they're messy, expensive. Proprietary solutions that just, you buy your way out of a problem quickly, but you create a new problem and it's painful. Factory, while it got us to where we are today, it's time to move beyond it. And my favorite, let's just skip that baby. So when it comes to the topology, we used to have traffic patterns, like I was talking about, 1 to 10, so relatively sane inside of the data center. But now the worst thing to happen to networking was Hadoop, which is extremely chatty. Microservices, the ratios of traffic that's staying in the data center is crazy. I've seen 1 to 10,000 plus, so for every megabit that goes out, you have 10 gigabits internally. It's really, really insane. You need better bisectional bandwidth across your network. This is where fat tree breaks down. And thankfully, we have CLO right now, which the vendors are calling spine and leaf topology. It's very, very briefly, it just allows all ports to be forwarding in the network. So you hash your traffic out horizontally as far as you go, as far as you can. Unfortunately, we weren't able to move to CLO until we had more fib space and routing capabilities, which we have now, so we can do it. And a quick rundown of the topology pros and cons. Fat tree and layer 2 are not the best thing for a modern data center. They're capacity reducing, basically. Automation, the lack of automation until recently has been problematic. It means your team needs to scale linearly, which is expensive. We no longer can buy our way out of problems. There's only the biggest box in the market has only got a finite capacity. If you hit that, then you need to do something else. And the lack of BGP to the server is going to cause issues with the containerized services we're seeing now, like Kubernetes. Luckily, there's pros. CLO is good bisectional. It should be a non-blocking. By another name, it will be known as crossbar matrix, so we're good there. Configuration, automation is the way forward. It's going to make things easier and predictable. Layer 3, top of rack, will allow us to scale horizontally from the very bottom to the top of the network and make it cheap. We can buy simple pizza boxes. They're very, very cheap, comparatively. We should at least try to deploy BGP to the servers or consider it for location, or for allow servers to signal location. So finally, we're going to get to the some conclusions I've had as a. The data centers are becoming absolutely less about the vendor. It's more about ports, protocols, ASIC, performance. It's fantastic, actually. It's like moving away from mainframes to pizza boxes like the systems guys did in the 80s and 90s. Server traffic is driving most of the capacity in data centers now, if not most of it. Cost is going down close to Moore's law. So speed is going up. We should see a 2.5x increase every 2 to 3 years now, which is nice. And ECMP has finally brought us to a place we can scale horizontally, but this is just the first step in a very long journey. We're going to see in the future that UCMP, unequal cost multipath, is going to drive a different topology, not just CLO in the future. Structure and predictability in the data center is the most important thing. Features don't really matter that much anymore. And something I stole from a previous team is predictability and intuition always beats memorization. And this is how we should always think. Configuration management is actually becoming mandatory. We can't afford to do things by hand anymore. We're fallible humans. We make mistakes all the time. I mean, I make mistakes all the time. We're converging on APIs, which is fantastic. I talked about OpenConfig. I really hope this is going to take off, but I imagine that we're going to see alternatives in the future. But the main thing is that we're still on the very start of this journey. There's still a lot of problems we need to solve. Right now, recovering network state from configuration is really hard. It's almost impossible. But taking data and dumping it into configuration is really, really easy. So, like I said, we're just starting a very long, interesting journey. Questions?
Questions? Not a single question? All right. Thank you very much, Rauiri.
I got a bonus cat for you guys.
All right, that leaves us with the little 7 minutes